And today I would like to start talking about measurements and calculations. So this is from textbook Chemistry for Today. It's the 6th edition, and we'll basically be going through the first chapter. And today I just want to focus on measurements and calculations. Right, and basically, this chapter, in part, is about working with numbers, working with measurements, and as scientists and engineers, people worry about how to report numbers and how to correctly do calculations using measured values, and there are a couple subtopics I want to bring to mind. The first is the concept of significant digits or significant figures. Okay, and then second is the idea of accuracy versus precision. Okay, now these aren't accuracy and precision aren't the same thing, and this is good background for you to know, since I believe Dr. Tammy Melton, the lab coordinator, is having you go through labs beginning this week. Okay, so that's the Chem 10-11 section. Remember, Chem 10-11 coincides with Chem 10-10, and you must pass the Chem 10-11 laboratory in order to pass the Chem 10-10 course. Okay. So accuracy and precision deals with the laboratory component. And then I would like to take you through the metric system, at least covering the basics of that system of measurements. That was first developed in France in about 1791 or so, and is used worldwide today. And lastly, related to the metric system, we'll close with some examples of how to convert between units. Let's say between a metric unit and the English unit. So, some of you, are probably familiar with cubic centimeters or cc's. For those of you who are nurses, how does that translate into ounces? I mean, there's a conversion. Ounces is also a fairly common way to measure volumes of liquid. Okay, so anyway, this is an outline for today's lecture. Okay, and so we'll begin with talking about significant figures, and then basically I'll just use some slang here, or some fairly common slang. Sig figs is often used, and when I say sig fig, that basically just means short for significant figures. Okay, or you might see it abbreviated as SFs or sig figs. Okay. Okay. Now, why do we go ahead and why do we report numbers in terms of significant figures? Well, first, what is a significant figure? Significant figure basically refers to the number of digits that you can confidently report a measurement. So let's say if you have a measuring stick like so, and then you have that looks like this, and you have something you want to measure here, let's say the length of this bar. So how do you report that? You report that as 1.4, 1.3. Actually, this digit in the tenths place is uncertain. Okay. No, basically because you're limited to the ability of this device to measure in the tenths place, and we can't do that. But for certain, we're pretty sure that it is at least 1 unit long. So let's just say, let's just call this inches. Okay, so this is 1.4 inches or 1.3 inches. You're not sure, and so we'll just say that we definitely have 1 sig fig. Okay, at least in saying that. Okay, we know that for sure. We know that digit for certain. However, if you were to get another type of ruler and that has, more markings so that you can be more confident in your measurements. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm kind of making this up. So if we are, if we use something like this, this is a more a better calibrated device here, where we can more confidently report this as 1.3 inches. Okay, and then so in this case, we have 2 sig figs. Okay, and the reason why we can say that is because we're more confident in this number, at least using this device. So significant figures basically tells us that inherently measurements are inexact, and then they're limited by the device itself. So each device, whether you have something that measures length or something that measures mass or weight, there's some uncertainty based upon how well these are calibrated. Okay, now now this is as opposed to something that is exact. So let's say there's one person, there's one of you. If you say like 12 or a dozen, okay, this is an exact number. Okay, so in other words, that's like saying, you have like 12. This number very certain. That this is very certain. So it's like saying this has like an infinite number of sig figs. For all practical purposes. So if you're reporting an exact number of something, that is it's also known as a discrete number. Discrete number. And there is an exactness to it. So when you're reporting an exact number of something, that's like saying that you have an infinite number of significant figures. Okay. Now this plays an important role when you do calculations later on. And I'll show you an example of that shortly. Okay. So so at least the take-home message with this is that when you're reporting a number, let's say a measured number, with measurements where there are a limited number of significant figures, with measurements there are a limited number of significant figures in measurements, because there is uncertainty associated with the device. And however, this is different than, let's say, if you have like an exact number, an exact quantity. These, for all intents and purposes, have an infinite number of significant figures. So since they're known exactly. Okay. Now, here's some things to note here. Suppose you have a number, like a measured number, measured quantity, that's this, okay. Now this is known as a leading zero. Okay. Okay, these are not significant. Okay. Because basically the reason for that is because this is simply a placeholder. It really doesn't tell you anything further about the accuracy of this. Now 1, 2, and 3, those are non-zero numbers. These are significant numbers, but these are not significant. So as far as accuracy, as far as reporting the number of decimal places that you can report this to, this doesn't count. Okay. Now, if you have a number that looks like this, okay, these are known as trailing zeros. Okay. These are trailing zeros. These are leading zeros. Now, because they appear to the right and then they have a decimal point, these are considered to be significant. Okay. So these are significant, these are not. Okay. Since this is a placeholder, the way this is written, like if it's written like this, then you're saying that you know this number with certainty. However, if you have something that is reported like this, I would say that this is ambiguous. Okay, so there's quite a bit of ambiguity here. I mean, of course, if you have a point like that, then you'd say there's 5 significant figures. But if you have this, and if you were to be a stickler about this, then you'd have to say that this is not significant. Why? Because this serves the same purpose as this. These are simply placeholders. Okay, that is if you strictly interpret this. I mean, it could be that you know this, but if you're writing it like this, then you're saying that there's uncertainty about this, these 2 digits, because they could be placeholders. So. Like for instance, like 100 is not the same thing as 100. Like if you say the word 100 or 101. I mean, obviously you're saying you know this digit here, but if you're just writing this, if you only have one significant figure, this number could equal that number because you're saying this is uncertain. But if you write it like this, you know that these are certain, and so anyway, it's but anyway, to avoid that the uncertainty in the reporting of numbers, some people simply just use scientific notation. If you write it like this, okay, then you're saying for certain that this is 1.23 times 10 to the third power. This has 3 sig figs. Okay. Or if you write it like this, 1.230, okay, this is this here is excuse me, this is a trailing zero here times 10 to the 3. This you're reporting that more exactly, so you're saying that has 4 sig figs. Okay, so we can summarize these observations in terms of a couple rules. So let me just go ahead and list those rules. Okay. 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 Rule number 1. All non-zero numbers are significant. All right. So let's say the number 22 here, right, has 2 sig figs. All right. The number 53.6 has 3 sig figs. Right. Okay. So that's rule number 1. Okay. Second rule Okay, the zero between numbers are significant. Okay, so the number 202 has 3 sig figs. Okay, the number 3.002 has 4 sig figs. So if you see a number and then there's a 0 between 2 numbers like this, I mean this is a significant digit, and these are significant digits. Okay. Okay. Third rule: the 0 beyond the decimal at the end of number is significant. Okay. Okay. So let's say 1.00. Okay. This has 3 sig figs. This has 3 sig figs. Okay. The number 2.23000 has how many? 6 sig figs. Okay. So like these count because it's beyond this decimal. Right. Let's say 50.00 has what? How many? 4 sig figs. All right. So anyway, these are examples that express this third rule. Okay, and then finally, number 4, the 0 preceding the first non-zero number is significant. Okay. So, example. Okay, this is the word is. Okay. IS. 0.00054. Okay. Oh, excuse me. I misspoke. I misspoke there. Is not. It's not significant. Okay. And the reason again, because it's these zeros here, they're placeholders. So if you have a number that's 0.00054, this has 2 sig figs. Okay, only this one and this one. So these other numbers don't increase the precision. 0.565 has what? 3 sig figs. Okay, so 1, 2, 3, right there. So note that this rule is in place. Just noting that zeros are placeholders. Okay, so these rules for certain apply. These are fairly universally accepted. Okay, all right. Okay, so those are the rules. Okay. Now, significant figures carry over to mathematical calculations. So whenever you're doing a mathematical operation, with numbers that have limitations in as far as how accurately you can report them, they also carry over. Okay. Now, when multiplying or dividing numbers, okay, the answer is limited to value with the least number of sig figs. Whoops, sig figs. Okay. Okay. Example. Here. Okay. So let's say we have a division here, 8.321. Okay. Divide that by 4.1. Okay. Now, if you were to plug this in your calculator will spit this out. 295,12195. Okay. Now, is that the correct way to report this number? At least as far as is this a valid way to report the number? The answer is no. Okay. Really, you have to report it like this. 2.0. Why is that? Well, it's because you only have two significant figures right here. You're limited to 2 sig figs. Okay, and if you're reporting all of these numbers here, it says that it basically tells you that something that's beyond what you're actually capable of measuring here. Okay, so that's just a rule that scientists tend to follow. We want to report the truth, but we don't want to embellish upon it. Okay, so anyway, this is just a way to keep us honest as far as doing calculations. Okay, so this is example 1. Let me show you another example that applies like an exact number with a measured quantity. So let's say you go to the supermarket or something, and you have 1 dozen eggs. 1 dozen eggs. Okay, and then so you want to buy these eggs, and they charge you by the gram, for example. So how many? How much would it cost you? So the calculation is done like so. So let's say we have 12 eggs times 1.234 grams. That's probably not a typical egg, but let's just say that for argument's sake. Now, if you were to plug this into the calculator, what would that show? 14.808 grams. One second, just a moment. I'm going to do this. 14.808 grams. Okay. So is this the proper way of reporting this calculated number? And the answer might surprise you. Well, basically, we have too many significant figures here. Okay, really, the proper way to report this is 14.81 grams. Okay, so and why is it 4 digits and not 2 digits here? Well, remember what I said before. This is an exact number. It's a discrete quantity. Okay, and discrete quantities, for all intents and purposes, it's like saying you have an infinite number of significant figures. So it's like 12.000000 repeating. So we are limited to the number of significant figures, not in this number, but rather this number. So this has 4 significant figures at most. So the answer must have at most 4 significant figures. Okay. Now, one can go, when you're having this discussion with a fellow at the deli, they might round this up to 15, like 15 grams, and And then you can say, hey, wait, you can't do that. I mean, this is 14.81. You know, when your scale or your calculations or whatever, you have to multiply 14.8, you know, times the price per gram. So at least you could save a couple cents on that. But in any case, this is the correct number of significant figures if you're to do this calculation. Okay. All right. So so basically, this is the rule for multiplication and division. That is, you know, you are limited to the answer should contain the number of significant figures of the value that has the least number of significant figures. Now, suppose you know, this were not a number, but you know, something else, like some other unit, you know, like a distance or some other quantity that you measure, like foot-pounds or force or something. Let's say you were multiplying, let's say 12, I don't know, I'm making this up, centimeters by 1.234 centimeters. Okay, so in this case, the correct answer would be like 15 square centimeters. So in this case, you're limited by these two numbers, right? Because this has two sig figs, because this is a measurement, that's a measurement. Okay, and therefore the answer has to have two significant figures. Okay, whereas over here, there's a multiplication that involves an exact quantity, a number, a discrete number, describing the number of items that you have. So, you know, that's why this is reported as 4 sig figs here. This only has 2 sig figs. Okay. Okay. So that's the rule for multiplication and division. Okay. Now, for addition and subtraction, interestingly, it turns out that the answer for an addition and subtraction could have more significant figures or less significant figures than the numbers that you start off with. Okay, so and really the best way to show this is by example. Okay, so anyway, just wanted to show you these notes here before I erase this and move on. Okay, I'm sure everyone has this now. Okay, now let's see, addition and subtraction. Okay, now let's do, so this is, let's call this example 3, okay? So if you add these two numbers, 1.9, and these are both measured values, 1.9 plus 18.65, what number do you report? What's the appropriate way to report this number? Okay, 1.9, 18.65, and I have to say, you know, you kind of have to keep track of the digits right here. Okay, so so the answer to this is 20.55. Now, is it correct to report it this way? Just leave it alone? The answer is no. Okay. The reason is because, like, we don't know the 100th place right here. I mean, there's an uncertainty with that. Okay. Really, the correct way to report this is 20.6. Okay, so that's how you report this number. Notice that the number of significant figures here, okay, is greater than 2. Okay, because we're certain. Although we're uncertain about this, we're fairly certain about this. Okay, so this is a minimum quantity that would be measured. We know that these would add up. So comparatively, when you compare this number with the number that has the least number of significant figures, we actually see an increase by 1. So this has 3 sig figs. This has 2 sig figs. Okay, so really it depends on how you know, how these places add up. Okay. All right. Another thing implicitly, and this is a rounding rule. Generally, by convention, scientists generally round to the nearest even number. Okay. They round in the nearest even number. So, for example, we all saw this. So let's say there's uncertainty in this digit right here. So we just simply say 20.6. Okay. Now, if it were something else, it were like 20.45. I just subscripted this just to indicate there's uncertainty in this number that needs to be rounded. This would be rounded like so, 20.4. Okay. So this is in the case where if you have a something that's you have a 5 there, how do you round this? Does this round to 20.6 or 20.5? Well, 6 is the nearest even number, so you round it to 0.6. 5 here, you round it to 20.4, 20.5. Well, in this case, 4 is the even number, so you round it to 20.4. Okay. And obviously, I think most of you know about rounding numbers such as this, 20.41. This rounds to 20.4. You got 20.48. You know, this rounds to 20.5. So basically, this is we've just executed a rule of rounding, rounding numbers. Okay. Okay. Okay, let's do another addition, subtraction example. Okay. Let's see, example 4. Okay. So actually, these numbers are taken from some exercises in your textbook. And so, let's say you add 1500 plus 10.9 plus 0.005. Okay, what's that number? Okay, so you basically have to kind of line this up. All right, and now, as I mentioned, you know, there's some like ambiguity, you know, when this number is written and there's no decimal place. So I'll just put a decimal there, okay, for this example. So right here, is this the correct way of reporting this final answer? Okay. Well, anyways, let's say no, it's not finished. How would you report this? You'd simply just report it as 1511. Why is that? Because, you know, this number right here, the uncertainty, there's uncertainty in the 10th place and the 100th place, so you don't know for certain. And then if you take this into account, you simply just round up. You just round to the to this place. Okay. So that's how that's done. Okay. Let's see. Let's do a subtraction problem. Okay. So 5.1196 minus 5.02, that's equal to what? Okay. So we have 5.1196 minus 5.02. Okay. If we do this, 0996. Okay. So do we report it like this? No. Well, basically, the correct answer, or the correct way of reporting it, is 0.10. Okay. And again, this is just mentioning that we know the 10th and 100th place for certain. We don't know about these digits. Okay, last example of addition and subtraction. Okay, let's see, 9.45 plus 0.73. Okay, if we line this up like so, 0.73, see it's 10.18. Okay, and actually that's the right way to report it. So we have we just leave this alone. Okay, so this accurately reflects how well we know these digits. We know them to the 10th place and the 100th place, and then we can say that because this is an addition, and since we're fairly certain of the large numbers, we're not certain about the small numbers. What do we see? We see an increase in the number of sig figs here. So this has 4 sig figs, even though this is greater than this. It's perfectly legitimate, since we're fairly certain about the larger numbers rather than the smaller numbers. Okay, so that's how significant figures are incorporated into calculations. Okay. All right. So we just talked about significant figures. The second point on our outline is accuracy, the difference between accuracy and precision. Okay. Now, accuracy deals with the ability to hit the target, to hit the true value. Okay, so what do we mean by that? So let's say you have a target, you have a bullseye, like so. You throw a dart, you hit the bullseye. So that's fairly accurate. That's because you can hit the target fairly well. Precision. What's precision? Precision is the ability to reproduce a measurement. Okay. So if you have something that you hit this and you're fairly on target, or if you have like an arrow that hits the bullseye, it splits the arrows. I mean, you could say that's fairly precise. And actually, that's the dream. That's kind of like the dream experiment that you hope to do. You hope to get both accuracy and precision. Okay, but a lot of times, that's not the case. A lot of times, the precision is based upon the ability to just to reproduce that measurement. Remember that example with the measuring stick here? You might have something that's calibrated this well, or something. I mean, I think you get the idea. So let's say if you measure something, one time you might read it's 1.3, another time you might read 1.4, 1.25, 1.6, etc. There is some uncertainty in this, and the uncertainty leads to the imprecision with that, as opposed to something that's calibrated more. When you measure 1.3 and then 1.3 again, then you're fairly certain that you can reproduce that result. So the precision is the ability to reproduce the measurement. Accuracy is how close you are to the accepted value. So certainly you can have various scenarios here in terms of accuracy and precision. You can have this one right here. This is accurate and precise. Okay, that's basically our dream there. Let's see, let me put this better. Okay, accurate and precise. You might have other scenarios where you have something that's precise but not accurate. Now, this isn't a bad scenario. To have something that's precise and not accurate, isn't totally bad, because it may mean that your instrument or your device is just miscalibrated. If you just calibrate it properly, you can probably get hit the target, hit the bullseye right there. Okay, but that's if you can't get something that's accurate and precise, at least try to get something that's precise. And if you can get something precise, maybe you can figure out what the glitch is to get things get a perfect experiment. Okay. Now the next scenario, which is more undesirable, is like so. You might get something that's accurate, but not precise. Okay, so there's the bullseye. Like, you hit it sometimes not, and because there's scatter in the data, so that means that there's an imprecision. You're able to hit the target once in a while, but there's something that's causing you to kind of miss the target. Okay, so that's accurate, not precise. Now, the absolute worst case scenario is something that is neither accurate nor precise. So you might see something like this. Okay, so this is neither accurate nor precise. You're basically all over the place. I'd say that you really have to go to the drawing board. It's probably you probably can't I don't know, you might just have to rethink your experiment from scratch. Okay, so anyway, those are the 4 scenarios of accuracy and precision. Get something that's accurate and precise, accurate, not precise, and precise and not accurate, and neither accurate nor precise. Again, accuracy describes the ability to get on target. Precision, the ability to reproduce that. Okay, and so those are not the same thing. Precision, stems from a lot of times stems from just the calibration of the quality, the calibration of the measuring device. Okay. Right. So that's accuracy and precision. Okay. Okay, now we are ready to talk about our third point, which is the metric system. Okay, and units of measurement are, they were basically created by human beings. They're created by us. And because of this, some of the measurements that we have are somewhat arbitrary. Okay, they're somewhat arbitrary, and the metric system basically had its birth in 1791 in France. It's part of the Système International, or you might know them as SI units. Okay, it's basically an attempt to try to unify different systems of measurement so that people from different countries, different places can communicate to each other. Okay, now just to give you an example of the state of the times back then, in the 1700s or so, people had different ways of measuring mass, like small amounts of mass. So, today, a little bit better at that. But let's say back then, there used to be a unit known as the grain, and the grain is literally defined as the mass of a grain of wheat. Okay, but however, it was an incoherent unit between countries. So let's say if you lived in France, you would have you would find that 9,216 grains equaled 1 pound. Okay. However, if you were in England, you'll find that 7,000 grains equaled 1 pound. And of course, you can imagine that there would certainly be some problems in communicating between countries, especially if you're doing trading. And so that was, at least one of the motivations for developing a new system. Okay. Now, another reason is to simply simplify calculations. Now, if you consider the English system, I mean, most of you have grown up with the English system. Let's see, we have an inch, which basically make up feet, and then make up a yard, and then eventually a mile or so. Now, look at the different names of the units which describe length. You got to remember an inch is, what a feet is, what a yard is, what a mile is. And actually, if you just try to keep all those in your head, it's just somewhat inconvenient. And another thing you have to remember is that like they're 12 inches to a foot. Okay, they're 3 feet in a yard, and there's so many yards in a mile. And these numbers are different. I mean, they're different numbers. 3. Like 12 inches, 12, and 3, and some other number that make up a mile. I mean, they're different numbers. They're not the same. So as far as doing calculations, it's just an inconvenient way to measure things. However, if you look at the metric system, we have the millimeter, a centimeter, a meter, and kilometer. I mean, you'll notice, the same word here, meter. Okay, and basically, there's a simplification in the units in that you're using the same base unit, and the only difference is you have a multiplier right here. So a milli is like 10 to the minus 3. It's like 1,000th of a meter. Centimeter is 1/100th of a meter. A meter is a base unit for length, and kilometer is means you have 1,000 meters. And so you can see that as far as calculations go, and as a scientist or engineer, you can do lots of calculations. It certainly helps in simplifying calculations. So generally, a metric unit consists of 2 parts. You generally just have a prefix, like a multiplier, and then you have a base unit, okay, that it's associated with. So, so you have a multiplier, and a base unit. Okay, so we were talking about length here. Meters, the base unit. Okay, so and in the metric system, there are various base units, depending on what it is that you are measuring. Okay, so if we draw up a table here, if we draw up a table here, if we're looking at length, the base unit here is the meter. Okay, for mass, although this is not intuitive, but the base unit for mass is actually the kilogram. Okay, so I mean, despite the name, but I mean, the kilo still applies. Like there are 1,000 grams in 1 gram. You might think that the gram is the base unit, but I mean, it turns out that the kilogram is a more convenient, sizable mass. Okay, so there is some arbitrariness in terms of this, but you know, at least this is an attempt to try to you know, make the units a little bit more convenient. The quantity measured in time is the second. Okay, and then temperature, the base unit, that is known as the Kelvin. By the way, this has the same magnitude as degrees Celsius. Okay, so you know, degrees Celsius, I mean, although the magnitude is the same, it's actually the Kelvin. That's really the base unit. Okay, and so all units, all SI units, are based upon these base units that I list here. So this is the base units. So like, you know, for force, energy, that kind of stuff, usually it's a combination of each of these units that gives rise to those more complex quantities. You know, we won't discuss that very much in this class, but you know, if you go on to Chem 1110, you'll probably encounter that, especially as some of you are also taking physics. You know, it'd be important for that as well. But we won't spend a whole lot of time with that. But just so you know that you know, the more complicated SI units has a basis in these basic base units right here. Okay, so these are the base units. Okay, and then the base units are combined with prefixes, and then on the exam I will test you on some very common prefixes. Okay. Well, by the way, just to give you an example, length, for example, is you know, if we're talking about a volume, that's like meters cubed. So this is so this unit of volume is a derivative of the length right here. So that's one example of how other units, considered more complex units, are derived from these base units. Okay. So anyway, on to talking about the prefixes. Okay, so here are the notes there in case you get them all. Okay. So. Now, now the prefixes that are used in the metric system are basically given in powers of 10. All right. So we have 10 to the 0 powers 1, 10 to the 2 powers 100. 10 to the 3rd power is 1,000, and this is basically for the base unit. Okay, all Well, I guess we're getting close to the end of time allotted for this session, so I will simply close by just listing the prefixes, one for the very large side and the one for the very small, and then we'll just take it up from there when I return, okay, in person. Okay. Okay, so that's the very large, this is the very small. Okay. Okay, so 10 to the 24th, the prefix for that is yada. Okay, I guess you may call it, I mean, I think that perhaps you should say lotta, that's a lot. And then 10 to the 12th is tera. 10 to the 9th is giga. Mega. Kilo. And hecto is 100, and then deca, DA. Okay, so that's the very large. I think many of you are familiar with this. These prefixes simply from computer terminology. You know, we have megabytes, gigabytes, terabytes. Maybe someday we'll have yottabytes. And but anyway, this is fairly. I think most of you are accustomed to this. All right. Now, on the other end, we have yocto, Y, femto, F, that's 10 to the minus 15th, as in femto, second lasers, we have that. Picoseconds, 10 to the minus 12. Nano, you may have heard of nanotechnology. That refers to things that are measured at the 10 to the minus 9 power of a meter. Okay. Micro, as in microcomputing. So this is an N. This is micro has the Greek mu. Milli, as in millimeters. And centi, as in centimeters. And then deci, okay, as in decimeters. Okay. So anyway, these are the prefixes that you basically just attach to the base units to get your metric unit. Okay. Well, I didn't get as far, didn't complete the outline for today, but when I come back, you know, we're out of time. We'll talk about conversions between the metric system to the English system, and we'll use the factor label method, and so that's the topic of discussion for next time. All right. So, so go ahead and read the chapter in the book. Let's say